So if you like, we can start again. We have been analyzing this system here, and the story I told you was a story based on infections. You could equally well tell the story about opinions that spread in social media or so. This is kind of a similar process. I want to connect it now to biophysics. So when you look at a cell, then you typically have a membrane, which is a surface. Right? This membrane is a lipid bilayer. I showed you some examples in the introductory lecture. And so this is 2D. And inside, this is the bulk, which in biology is called the cytosol, because it's a gel-like structure that defines the interior of the cell. And that's 3D. And now let me idealize that just to a little section of the membrane and the corresponding cytosol. As you know, biology is determined by DNA, and the workhorses are proteins. So these proteins, you can visualize them, say, as little particles, 10 nanometer in size. And this protein particle here in the cytosol I call C. That was actually the original reason why I picked the name C. So that's the protein that's residing in the cytosol, in the interior of the cell. And there could also be the same protein could just attach to the membrane. So you would have attachment here with a certain rate. And these rates can be spontaneous. That would be somebody gets sick spontaneously. That's not what we have there. But for a process of a protein attaching to the membrane, this could be spontaneous. Just goes there by diffusion and then gets stuck. And then it's on the membrane, and I call it M. If now this protein is on the membrane, there could be nonlinear processes that could have various reasons. I don't specify them right now, such that if there is something on the membrane, there is a positive feedback such that you recruit more of those proteins to the membrane. That corresponds to this process that I have here on the board. So if something is on the membrane and there's a protein in the cytosol nearby, then the protein on the membrane recruits the protein in the cytosol to the membrane. That replaces the infection process. Okay, so infection in the contact process would then be the same as recruitment to the membrane. Okay. When these proteins are on the membrane, they can also detach. Right? They just unbind from the membrane, go back in the cytosol, and live there. This corresponds in the scheme that I have there to the recovery of the sick individual. So you have a similar type of dynamics. You have proteins that are recruited to the membrane and go back. And that means you can have a dynamics here where you transfer proteins to the membrane and back. And this can give rise not just to switching of populations between cytosol and membrane. As we will learn later in the lecture, this can also give rise to all kinds of interesting patterns that form on the membrane. So here is one of those examples. This is budding yeast, where certain proteins, they're called CDC42, they are going to the membrane. Then once they are recruited, there's some diffusion and reaction that gives rise to pattern formation. And usually when you describe these kind of processes, they have a function. And the function I alluded to earlier in my motivational lecture is that where you have those patterns on the membrane, you have the formation of actin cables, so polymers, and these polymers in the cytosol then push out the bud side and give rise to a new offspring. Now, when you look at these reactions that give rise to pattern formation, they're actually pretty complicated. I think I explained that a bit, but this one here is actually the one for yeast. So it's very complicated, at least for a physicist. There is a protein called CDC42. It's again in an active and an inactive state. There are proteins that are called BEM1. There are proteins that are called GEF. There are proteins that are called GDIs, etc., etc. And it's the task of biochemistry to really figure out how these reaction networks work. And if you want to describe a biological system in detail, then you have to worry about these reaction schemes. What we'll do here in the lecture is to make things simple first, so you understand the basic principles before we would model something as complicated as this. So you can go to a conceptual model, and this conceptual model is what I have here on the board, right? I have just one protein, and I have it in two states, either in the cytosol or on the membrane. So when I now write down the equation of motion for that, then I can write dtm equals something and dtc equals something. Before we had a specific case, so remember this was lambda mc minus delta m. Now I just say I'm writing here f of mc, an arbitrary function that somehow encodes all these reactions that I have here and that you may consider as some kind of low-dimensional projection of the more complicated reaction schemes that we saw on the previous slide. Now there is to be something here as well, which needs to be what? Minus, yeah. So it needs to be minus f of mc. And that is because you have mass conservation in the system. Okay, and that's key. That's really key. It looks like something which is minor, but mass conservation in the system opens up a very important way of controlling the system. And let me note it down already here. So n, the population size, is a control parameter. You saw this previously. So when we discussed the infection model, the outbreak of an epidemic depended on how large the population size is. So as you control the population size, you can make things have a bifurcation. And here, controlling protein number is something which in biology is quite natural because you have DNA, and on DNA you can read off the information on that DNA and you produce proteins. So as you change the production rate of these proteins, a cell is able to change the population size of these proteins and thereby possibly can go through bifurcation points. And those bifurcation points could, for example, trigger in the spatially extended systems pattern formation as you saw it. This whole theme of conceptual one-dimensional models, two-component models, in space has a long tradition. So if you look at those equations and you add diffusion to it, then it's a very famous set of equations that was written down by Alan Turing in 1952 in a paper which he called The Chemical Basis of Morphogenesis. And it's also the advent of people working on pattern formation in biological systems. And that's why many of the patterns that we see just were named Turing patterns after this really groundbreaking work by Alan Turing in 1952. And he had those equations. So dTm is F plus diffusion, and dTc is G plus diffusion. That's not what we have. We have F and minus F. Okay? And that's different. If you have F and G, that means the population that you study of M's and C's is not conserved. There's some kind of production and there's some kind of degradation. And as we will learn again later on in the lecture, if you have production and degradation, the physics is different from the physics when you do have mass conservation in the system. So let me come back to the case where we have mass conservation and study that. Okay, so we do have this set of equations, and this is then entitled two-component systems with mass conservation. Good. So let me first talk about this function f a bit more. So f of m and c has, as I explained it here, two characteristic parts. You shuffle things from the cytosol to the membrane and you get them back. So the structure of this function is typically such that there is a function a of m that depends on the membrane concentration times the cytosolic concentration. Okay, and this could be a constant, and then it would just be attachment, and if it's some function of m, it could be recruitment and all these things. And it's always proportional to the cytosolic concentration because that's what you transfer from the cytosol to the membrane. And then similarly, you have things that are on the membrane and detach with some rate d of m, and this then has to be proportional to what you actually already have on the membrane, so the concentration m. How could this look like in more detail? So let's write this down now in chemical rates. So I said before, when you look at such a process, there could be a attachment process that just happens autonomously without any kind of feedback. And that would simply be a K on times the cytosolic concentration. Okay? Something spontaneously goes from the cytosol to the membrane. And then we can have terms. This is now again some kinetic parameter, which says K feedback, FB. And this will depend on the concentration on the membrane because you want to create feedback, positive feedback. So you can have some function of m that you write here. And we could take a linear function, but let's take a nonlinear function because then you have richer behavior. So what I take here is something that increases like m squared. So there's a strong feedback, and it not just increases linearly with m, but quadratic in m. And now you say, of course, if you have some feedback mechanism that brings stuff to the membrane, this feedback mechanism should saturate at some point, because chemistry is limited in the way what it can do. So let us write this as some kind of parameter that's usually called KD value plus m squared. And that means what you have here, right, is something that starts quadratically and then saturates. That's the kind of function you describe by such a feedback mechanism. It's increasing and then saturating. And the value where it starts to saturate is fixed by the KD value, and the amplitude of the effect is set by the feedback rate. Okay, and then you have minus, and here we make our life simple. We just say this is only a spontaneous off rate, so it's a constant k off, a kinetic rate k off times m. All right. Now, what you can do here is that you can non-dimensionalize that. So if you look here on this equation, it's dt times concentration is F. So if I have something like k on times c, this k on has a dimension of 1 over time. Now, what we can do is we can rescale time. So we rescale time t and use, for example, now what do I take here? K off to the minus 1 as my basic time scale. So my units in which I measure time. And that then means, and let me do this here by just dividing through. That means you divide through here by k off, and similarly here you divide through by k off. And then this object that you have there, right, this is now a dimensionless parameter, because it's comparing two different line scales, and let's call this kappa. Okay. So that's actually very important when you study these nonlinear dynamic systems. You should first always rewrite things in dimensionless variables, because that teaches you really what are the independent parameters in the system and what's just how you measure time or space or so, right? So this is key in order to rewrite things. Now, if you look here, we have another choice that we can make. Do you see it? We can choose the units in which we measure membrane concentration. So we can just say we put kd squared equal to 1. Right, so we do kd squared is set to 1, and that corresponds to choosing units for concentration. Right, so let's put here A1. Now, this here is still then a second dimensionless parameter. So we have here one dimensionless parameter, that's the second one. And for simplicity, and that's now a choice I make, I say for simplicity, let's just look at the case that KFB divided by K off is equal to 1. So that's a choice that I make. And then when you have such a theory now that you want to analyze, you can study it as a one parameter family. So kappa is your control parameter that you want to vary. Okay? In addition to what? What's the other control parameter that you have? N. Okay? So here, this is a control parameter. And of course, also here, N. That's the other control parameter that you have. So very good. Now, how does this typically look like? So what I'm plotting here is C as a vertical axis and M as a horizontal axis. And there's this particular line, this one here, f of M and C equal to 0. That's the Nullcline. It's a very important concept. It's just the set of equilibrium points in the very same way as before we had the surface of equilibria for our Ginzburg, for our Landau problem, and that's f of mc equal to 0, and that just means that we are at a fixed point, right, where dtm and dtc are both 0. So it's a line of fixed points. And we can determine this line of fixed points by just using the relation that I wrote down. So if I invert that relation, you get C equals M divided by kappa plus M squared 1 plus m squared. And you see that why this function has some n-shaped. So at small m it starts linear, then this term kicks in, and that makes it go over a hump and down. But ultimately, if m is large, that term again is a constant. So you go over from m over kappa to a linear slope m over kappa plus 1. And that's what you see here. This function that you have here starts linear, it goes over a hump, and then ends linear again with a different slope because the denominator has changed. Those n-shaped nullclines are very typical. And they give rise, as we will learn, to quite a range of interesting behavior. One fact you also need to account for. So if you just look at the nullcline, the set of equilibria, it's a set. So it doesn't determine what equilibrium you actually have. You need a second condition that fixes the equilibrium. And in our case, right, it is the total density n that fixes the equilibrium. So if you have a density n1, n2, or n3, it will flow in these subspaces, right here, which are mass-conserving subspaces. In this subspace, the flow has to happen. It cannot get out of it because you have to conserve the particle number. So it's that part of the phase space in which reactions can drive you between different points. So now that you see that, let us analyze stability. So for that, we rewrite first the equation as an equation for m alone, because we do have the conservation law, right? And therefore, we can write it as f of m. And then here for c, we write n minus m. Okay, that's the equation then we have. So we have, again, a one component ODE. And one component is the flow here along these different lines that you see in phase space. So how would you do that? So let's look at stability. So let's say we have a fixed point in our system, and we want to study deviations from a fixed point that we call m star. What these fixed points are, you can read off here, right? Here's one fixed point, here are three, here's again one, and we don't know yet from looking at it which one is stable and which one is unstable. So what you can do, though, is that you do a linear stability analysis, meaning you expand around a fixed point, and you want to know then what is the dynamics in the vicinity of that fixed point. So you write this as m equals m star plus delta m, and here as well. And now, since this depends on two arguments in that function, you have to take, as you Taylor expand, the partial derivative with respect to m, and then the partial derivative with respect to c. That means you get fm minus fc here for the linear term, because there's a plus and here minus, and fm and c, they are just shorthands of df with respect to dm or c evaluated at m star c star. Okay. So you get this from the Taylor expansion, and then here you just get the delta m. So you get m minus m star, and let me explicitly indicate that the value of that fixed point is parameterized in terms of the total number of individuals that you have in the system. Okay, so this is delta m, and that means this is like an eigenvalue of the system, sigma, that depends on n times your delta m. That's our eigenvalue. And that eigenvalue is fm minus fc. Fm minus fc has a geometric meaning. And let me explain that to you. So let's say we look at the slope of the Nullcline. So I'm writing this as c star of m evaluated at a certain value of n. What I'm doing here is, right, I'm looking at this function c star of m, and I want to know what's the slope of that function. You see what the slope is, but we can express it in terms of partial derivatives of the Nullcline line that you have here. So, and it's quite easy to show that this is minus fm over fc at constant n. So the ratio of these partial derivatives with a minus sign is the slope of the Nullcline. And that's basically what you have here. If you pull out one of those, then say fc, then you have 1 minus fm over c here in the interior, and you can then relate the slope of the Nullcline that you have here with the eigenvalue. And that's very important, because what you do by doing this is that you connect an analytic expression that you found just by doing a Taylor expansion to a feature of the geometry that you have in phase space. And remember, this is a major theme of how you analyze dynamic systems. You would like to understand things not just in terms of analytics, but basically really in terms of the geometry of the flow in the phase space. Okay, so for specificity, we look at the case that fc equals a of m greater than 0. You could look at other cases, but they would be, analyzed in a very similar fashion. And here, because I already wrote it down in this generic form, you have an attachment rate times c. And of course, an attachment rate has to be positive. Okay, so for that particular form of this arbitrary function f, fc is a positive quantity. So as you have that, then this condition that you have sigma of n less than 0 is the same as the condition that minus fm divided by fc is greater than minus 1. Okay? Because this here then is 1 minus corresponding fm over fc. So now what does that mean in our graphical representation? Minus 1 is the slope of our mass-conserving subspace, right? So if the slope of the Nullcline is such that it cuts the mass-conserving subspace from the bottom, then this condition says you have a stable fixed point. If, however, it cuts the mass-conserving subspace from the top, then you violate this stability condition, because the slope is then steeper as the minus 1, right? That means simply, if I go along this Nullcline, every time I construct the tangent, if this tangent has a slope steeper than minus 1, I'll put a dashed line. So this window here is a window of unstable fixed points. Right? And then you see what happens. So as you go through and change the control parameter, that is the external, the mass of proteins in your system, you go from one stable fixed point to a corresponding bifurcation into 3 stable fixed points with 1 unstable and 2 stable fixed points. So what is that? Saddle node, right? That's a saddle node bifurcation. And then you go back to another monostable situation. You can flip the full phase diagram as we do it here. Right? You just, instead of plotting M, you plot N, which you can relate to M simply by adding M and C. And then you get a fold, very much as the fold that we had before in the case of studying the Landau model. And there you explicitly see how this happens. So the fold goes back in a saddle node bifurcation if this stability criterion is obeyed. So meaning here if the Nullcline overcuts the mass-conserving subspace, which happens when, as a function of n, this function c star of n has a vertical tangent. Right? Yeah?
Sorry, why does the attachment rate has to be always positive?
If it's a rate, okay, so a rate is a probability per unit time, and that's why a rate has always to be positive. If you want to have something negative, you say you have detachment. And that's what I wrote here, right? I'm saying there's also the opposite process where I lose particles from the membrane to the cytosol, and I'm saying I'm losing it, so I have a function that has minus a positive rate times the concentration on the membrane. Okay? But rates have to be positive because they're probabilities per unit time.
So what has to be positive is the A, not the A.
Yeah, the A. Did I write this? So A is positive and D is positive. And C and M are also positive because they're concentrations. They can't get negative. And the minus here says in which direction the process goes. Because this is math, right, I could study just this as a mathematical problem without talking about the physics or biology of it. And then the function I have could have the feature that FC is not positive but negative. And you can study this for your own. It's just studying different cases and you get similar behavior. Okay, so a few names here. These objects that we introduced here, this is a Nullcline. This is a reactive phase space or mass-conserving plane in red. Only there reactions can happen. And these mass-conserving subspaces are defined by the simplex n equals m plus c. Good. Now, let's do linear stability analysis in a different way. You have seen linear stability analysis done like so. So on the screen, that's what we studied on the blackboard. I've already shown you how this works. And now to close, I would like to do with you a linear stability analysis that's a bit different than that. So remember this. And now let's go to a different stability analysis. So here we have C, here we have M, here we have M of M and C equal to 0. That's our Nullcline. And let's say we do have a point somewhere here, which is M star and C star. That's a fixed point. So I showed you I can do linear stability analysis, but just projecting it to the mass conserving plane with M plus C equals to N. But you can also analyze it in 2 dimensions. And that has an advantage, as you will see. And later on, when we do the spatially extended system, this will become even more important. So let's define deviations or perturbations now as delta M being M minus MC and delta C being C minus C star. And that defines this perturbation vector delta U. Then you can write the equation that we have as a Jacobian times delta U. And that, of course, you know from your course in analysis, in multidimensional analysis, as you do a Taylor expansion around a point, that is an extremum, which we have here. The first non-trivial term is the Jacobian times the deviation. And the Jacobian is the matrix composed of all the partial derivatives of your function with respect to your variables evaluated at the fixed point. So in our case, this is FM and FC. And then the second line is trivial because it's the same kind of problem, just with a minus sign. So you have minus FM and minus FC. And then this problem is a 2x2 matrix, and you have to calculate the eigenvalues of that matrix and the eigenvectors of that matrix. I guess that's a trivial exercise. You can do this in your head. There is one eigenvalue, which is 0. And there's a second eigenvalue that is Fm minus Fc. Okay. Why should that not surprise you? Because we have calculated one of them, which is Fm minus Fc. Okay, so we recover that, and we should. What's the 0? Okay, I'll show you the eigenvectors that correspond, not normalized necessarily. So the eigenvectors that we have is Fc minus Fm. And the second eigenvector that we have here is 1 minus 1. Okay. Second eigenvector is easy. 1 minus 1 is the simplex. Right? So this is the eigenvalue in the direction of the mass conserving subspace, or the reactive subspace as I called it. And that's what we did before. We stayed on that subspace by construction. We only allowed deviations in that direction. Now what is that vector? So f equal to 0 has a normal, which is the gradient of f. And gradient of f is fmfc, and this here is the tangent, right? This is the tangent to the nullcline. And for the tangent to the nullcline, the eigenvalue is 0. Reason being, right, so go tangent to the nullcline, meaning you go from here to here. If you move to here, is there restoring force? No, you are on equilibrium point. So as you go along equilibrium points, there is no eigenvalue that's non-vanishing. It has to be 0 because you are now, there's nothing that pulls you back as you go on the nullcline. So this is sigma equals 0 along the line of equilibria, that is the nullcline. All right, and with that, I'll close for today. And next lecture, I will then go to real two-component systems where you can't do that. And then we have to analyze what's happening with a 2x2 matrix. So if you feel that you need to read up on this, just read up on eigenvalues and eigenvectors of also linear algebra problems. Good, thank you.